fall with and without air resistance from Sophia Hadier, Physics 2211. The purpose is to model the motion of a falling object using physics principles and compare motion with and without air resistance. A preview of the results: without air resistance, object accelerates constantly. With air resistance, acceleration decreases over time, and the result is an object with drag falls slower and reaches a lower velocity. The physics principles used are Newton's second law, F net equals ma, which is net force. Forces in the system: gravity pulls downward and air resistance drag opposes the motion of gravity. Systems and surroundings: the system is the falling ball and the surroundings are earth, which is gravity, and air, which is drag. The equation for gravity is Fg equals mg, which means gravity is constant. The drag force is F drag equals negative bv. Drag depends on velocity. As velocity increases, drag increases. And Newton's second law is F net equals Fg plus F drag. Model assumptions: the object is treated as a point mass. Motion is only vertical in one dimension. Constant gravitational field, where G equals 9.8 meters per second squared. Linear drag model is F equals negative V. No wind or turbulence. These assumptions simplify the system while still capturing the main physics behavior at play. The initial conditions: the initial height is 5 meters, initial velocity is 0 meters, the mass is 0.2 kilograms, and the drag coefficient, which is the B value, is 0.1 for the drag case. Two cases are simulated: no air resistance and with air resistance. This is the code used for the computational model. On the left are all of the initial factors, and on the right is the simulation loop. This is the simulation output. On the left is the graph, which observes no drag as a straight line, constant acceleration, especially for the velocity. So the green line is straight, and with drag there is a curve. So the purple line, there is a curved motion. And the simulation observation, the red ball on the right falls more slowly due to drag. The analysis: the similarities: both objects accelerate downward and both follow Newton's second law. The differences, however, are drag reduces net force, so lower acceleration with drag, and velocity increases more slowly, which can be seen from the graph. Sources of error: linear drag is a simplification. Real drag is vaguely equivalent to velocity squared. The time step approximation could be cause for numerical error, and assumed constant air properties, which are not the case in real life. These cause small differences from real-world motion. The what-if questions: what if drag coefficient increases, the objects fall even slower? This would be kind of simulated through thicker air. What if mass increases, less effect from drag, falls faster, so a heavier object is less affected by drag? And what if gravity changes? For example, what if we drop them on the moon with the same air resistance? The lower acceleration would mean a slower fall. What does this mean? Air resistance plays a major role at higher speeds. The real world motion is rarely ideal, and simple models can still predict behavior well. Conclusion: successfully modeled free fall using physics principles, demonstrated effect of air resistance, showed agreement between physics theory and simulation. The main takeaway: air resistance reduces acceleration and limits velocity.